In this video, I'm going to be discussing Lab 6, which is nuclear radiation. Again, this is also going to be another simple, quick lab. Nuclear radiation is basically occurring in the nucleus of an atom, where the nucleus is disintegrating. All right. Now, all elements have some amount of radioactivity associated with it. Some a lot more than others. Others are a lot more stable. And all elements have isotopes. So how do you define an isotope? An isotope has the same number of protons, all right? So hydrogen, for example, it has one proton, which is why it's hydrogen. Now, there are hydrogens with different numbers of neutrons. So, for example, hydrogen, as we know, the hydrogen gas or hydrogen atom, the commonly occurring hydrogen, has one proton but no neutron. There's an isotope of hydrogen called as deuterium, which does have one proton and one neutron. So it's slightly heavier in terms of mass compared to the hydrogen atom, all right? And then there's yet another isotope for hydrogen, which has one proton, but it has two neutrons. So you can see that the constant in all of these hydrogens is the one proton. And that's why they are the same element, all right? The protons are the identity of the element. So they have, all of these isotopes have the same number of protons, which is why they're all different forms of hydrogen, but they are differing in the numbers of neutron, all right? So deuterium is going to be heavier than ordinary hydrogen by 1 mass unit, and tritium, which is the other isotope, is going to be heavier than the ordinary hydrogen by 2 mass units, because it has 2 neutrons, including that one proton, all right? So isotopes are the same elements, like I explained with hydrogen. The only difference is the mass, all right? Hydrogen has a mass of 1, but deuterium has a mass of 2, and then tritium has a mass of 3, all right? And the reason for it is because of the different numbers of neutrons present in these isotopes. So some of them are unstable, and the nucleus tends to break up spontaneously. Some can be induced to break up, all right? So all of this radioactivity happens in the nucleus as it starts breaking up, all right? And so when it does, it emits energy and particles, and this is called as radiation. And because these nuclei, plural nuclei, are emitting radiation, they're called as radioisotopes. Some of the radioisotopes might exclusively emit a particle called as alpha rays, right? These are heavy particles. They do have a positive charge, okay? And they are heavy, so they're not able to travel very far in the air, all right? And because they can't travel far, they also don't penetrate much, all right? So if you just have a piece of paper or even skin, clothing can stop them from going any further, all right? Other isotopes might emit high energy electron-like particles called as beta rays, right? So these are negatively charged electrons, and they travel 100 times further than the alpha particle, so they have more penetration, all right? And then you have gamma, which is just energy. There's no particle nature to it, just pure energy. So they're kind of like X-rays. They're highly penetrating and therefore they're very damaging. All right. So in terms of damage, alpha would cause the least damage as long as you are wearing protective clothing, just ordinary clothing. Beta radiation, if you wear like gloves and a lab coat, that's enough to stop it. Gamma radiation, on the other hand, like X-rays, penetrate really far. They travel very far because it's just energy, and therefore you definitely need to have lead apron or something like that. Concrete lead helps to stop gamma radiation. So some of these radioisotopes, like the technetium metastable, emits gamma radiation. Now, this particular radioisotope is used a lot in medicine because of the fact that you can use it to detect and diagnose different diseases. So, how do you measure this radiation? How do you measure this radioactivity? The instrument is called a Geiger counter. So what it does is it takes that radiation and converts it into electrical units, and then that is registered like a clicking sound, right? So each of that click is a unit of radiation. So most times there's always going to be background radiation. There's low levels of background radiation found everywhere. Now it depends on the amount of pollution in a country. If the pollution is well controlled, the background radiation is relatively low. But however, if there's a lot of pollution, then of course the background radiation goes up. Radiation found in the soil can then seep in through, like especially the foundation of old houses, and it can accumulate in the basement, right? Even everyday objects that we touch or use are emitting radiation. So it's all around us. The highest amount of radiation actually comes from the stars and the supernovas, etc. They're called as cosmic radiation. All right, and the sun too. There's a lot of radiation being emitted, especially all that UV rays, etc., coming from the sun. So some of this cosmic radiation is penetrating the atmosphere and reaching the Earth's surface. However, the ozone gas is helping to prevent some of that really penetrating radiation from reaching the Earth's surface. Otherwise, it would lead to a higher level of radiation on the Earth's surface. And so you must have heard of that hole in the ozone layer that could lead to things like the global warming, etc., because there's a lot more radiation coming onto the Earth's surface than might have been had not there been the hole in the ozone layer. All of this radiation is the background radiation, and it can vary from location. Like I said, if there's more pollution in a place, it'll be higher. Less pollution, it tends to be lower. Also, it tends to, the heavier radiation, like radon, can accumulate in the foundations of old buildings. So there's always going to be an inspection of the basements done on a regular basis. And there are going to be, the health inspectors are going to always check for radiation levels. So here in this experiment, we're using a Geiger counter to first record the background radiation in the first part of the experiment, And then afterwards, you're going to test out different samples and check what those results are. So when you record the value for the radiation for these different samples, you have to make sure that you subtract the background from each of the recorded radiation. The units of radiation is counts per minute, or CPM. So the first part, as I said, is taking a Geiger-Müller counter, and then from the instrument shelf, placing it on your workbench, turning it on, and then recording the background radiation in CPM. All right. And once you have that background radiation, you move on to the second part of the experiment, where you are testing first an alpha source, a beta source, a gamma source, all right, and then some common everyday objects like a smoke detector. All right. So first you're going to check a smoke detector, an intact smoke detector. That means the one that has the plastic cover like you see in your house. And then you're going to check the source inside the smoke detector. That means minus the plastic cover, the actual source of radioactivity in the smoke detector, which is americium-241. All right. So after that, you're going to then when you do this background radiation check in the lab, especially in the virtual lab where the level is going to be pretty low, it's a controlled environment, and it might register in the range of 40 CPM. After that, you're going to check some everyday objects, including just the alpha, beta, and the gamma sources. And then a lantern, mantle, fiesta ware, glow light, salt substitute, smoke detector, and then after removing that plastic cover, just the source of radiation inside the smoke detector, which is the americium-241. All right. And then in each case, the actual recorded radiation is minus the background. All right. So you're going to subtract 40 out of each of these. So this would be the actual recorded radiation. Now the thing that all pops out is the source inside the smoke detector is pretty high, the amount of radiation. All right. 10,000. But once you have the cover on, all right, the intact smoke detector, it goes down to 0. All right, which is why they ask you to make sure to check that your smoke detectors in your house periodically, the covers are intact and they're not broken or cracked. The other thing that stands out is the lantern mantle, which is around 8,000 CPM, right? So the americium-241 is pretty high, followed by the lantern mantle, which is 8,000. And comparing alpha, beta, and gamma, you can see that the beta particles source seems to have the highest 16,300. Right? So what is the difference in radiation between the intact smoke detector and just the source? You can see that that plastic cover makes a world of difference. Without the plastic cover, it's very high. With the plastic cover on, it goes down to 0. So where does radiation originate? In the nucleus of an atom, right? We need to protect ourselves from radiation exposure, otherwise it'll lead to tissue damage, and of course in extreme cases of exposure leads to death. And I will stop here and continue this in the next video.